a little nicer. All right, so vector valued functions, we've actually been talking about them for quite some time, just in the context of lines, but you could have a vector valued function that represents any sort of function, right? So what we're going to do is talk about, the more popular ones, right? So we have circular functions, we have any other variation of a conic section, they come into play here, right? But the idea is to be able to represent functions in 3 dimensions, but we're going to run into the same issue that we did when we're dealing with a line. If I try to graph a line, a parabola, for example, like y equals x squared, it's going to assume that it's for all values of z. So it's going to give me a parabola that's got infinite height and depth, right? So it's going to look more like a folded or kind of like a bent sheet of paper than just an actual parabola. The top view would look parabolic, but it wouldn't actually be a parabola. So we still have to use parametrics even when it comes to coming up with the equations or the graphs of other types of 2-dimensional functions in 3 dimensions. That's really where the idea of parametrics becomes powerful, because it's the idea that we can bridge dimensions, right? So parametrics allow us to cross dimensional barriers, if you will, going from 2 dimensions to 3 dimensions to 4 dimensions, right? And so on, right? So that's really what this whole page is talking about. So feel free to read that in more detail, but what I'm going to do is I'm going to just take you through the mechanics of sketching parametrics in 3 dimensions. We'll start off with a quick review of a 2-dimensional case, but then we'll go into 3 dimensions and so on. So, because we're going to incorporate the calculus pretty soon, and that's where it all starts getting interesting, right? If it wasn't already. So the first one there, we're talking about 2 linear models here, right? So we have 4t minus 1, and then also 2t plus 5. So just going right on back to the first class, maybe second class. I don't even know if it's a straight line. Can't draw a straight line. It's just crazy. I'm just going to live with a line that's not straight. So I need some t values to work off of, but since it's linear, I can just kind of go with what my gut tells me. So I'll just kind of circulate around 0. So 0, -1, -2, +1, +2. We could actually use Desmos to our advantage here. So let me pull up Desmos actually. But like the other, the ordinary Desmos, the Desmos graphing calculator. But if you do this in table form, so we have t, 4t minus 1, and 2t plus 5 for our different components. If I use the table function, I can type in -2, -1, 0, 1, and 2. You see, it recognizes that I'm doing it in a particular order. I can also change this to whatever I want. I'm going to change it to a t. Make this, hop me back there, 4t minus uno. And it runs the calculations for me, and then 2t plus 5. Oh, hit the wrong thing. And so we have this set of ordered pairs here. I can just jot them down. So -9, -5, -1, 3, and 7. Computing it in your head wouldn't have been even remotely difficult, but I just wanted to show you this technique so that when they get a little spicier / in the next example, you'll see that there's an opportunity for you to use the technology. So each one of these ends up being an ordered pair. All right, but it's a vector valued function. So yeah, it's an ordered pair, but I want the vector that corresponds with -9, 1. The vector that corresponds with -5, 3, and so on. All right, so when I'm plotting this, I'm not just plotting coordinates, I'm plotting vectors. All right, and the vectors are going to serve as kind of like supports for the line. You think of the line as like a highway, and the vectors themselves will serve as the supports that hold up that highway. So -9, 1. Corresponding vector. All right. Then -5, 3, 1, 2. I'll plot the points all first, and then I'll get into the vectors. So these would all have to be there. And this would be the path of the line that is traced out by the movement of those vectors. All right. So it's the vectors themselves that generate the R of t. All right. The points that are traced out by the ends of those vectors, that actually happens to be a line, but that's not really the point. All right. This is the set of all possible vectors. So if you, I mean, these are the ones we focused on in our table, but if I wanted to, and I suppose I do because I'm doing it, we could include infinitely many vectors, you know, kind of thinking of the span of a bridge on whatever the interval is. Oh, that moved on me. Get out of there. So all of these vectors are what R of t is giving us. All right, so you can imagine that coming up with the slope of a tangent in this context is going to be a little bit more challenging than it was before. All right, because if R of t isn't actually the line itself, then what are we getting if we were to take the derivative of that function R of t? That's the big question, and that's going to be the subject of class next time, right? But for now, we're just practicing the skill. All right, so all of this stuff, again, I'm just kind of circle it for you. And get it in there. All of that, that's your R of t. Right? And again, it just so happens that the endpoints of those vectors trace out a line, but it's the movement of those vectors. That's the definition of R of t. Mm-hmm. So when we're sketching out R of t equals equal to cosine 2 sine and then t, you know, like the first two parts of it have, you know, an elliptical feel when you think back to parametrics from the first unit. But in a vector valued function, again, it's the vectors that we care about, but also there's that t component that's gonna be a, you know, a monkey wrench in the mix. Right? So I'm gonna need 4 columns here. all operating under the assumption that we can come up with nice enough values to make this all work out. Right? So, because we have a mixture of trig and not trig. All right, so that's something to keep in mind. So it's going to seem weird when I write this, but I'm going to bookend it with t, because t is a parameter, but also t is part of the function itself. All right, so 2 sine t and then t. So it's really going to be these ordered triples that give us the path created by the vectors. All right, so that's kind of what we're focusing on. But I still need some t values. Now it's a question. It's like, well, where do I want my convenience to lay or lie? You know, do I want to have nice t values and have ugly cosine values and sine values, or do I want to have the nice trig functions and the ugly ugly parameter? You know, my school of thought, or the school of thought I subscribe to, is make the trig as convenient as possible and then go from there, right? So what I would do here is new blank graph, would make a table, and my table would incorporate t values that are convenient for sine and cosine. So again, t, just to make it look the part. I want cosine of t. I want 2 times the sine of t. And then again, just for good measure, I'll have the t in there. Okay. Now this is all reliant on whatever that first entry is, that first column entry. Well, seems like that putting the t in there just kind of messed things up, so let me get rid of that. Might be a circular logic thing. So start with a 0. All right, so 1, 0, 0. Then the next convenient one, by my reckoning, is pi over 6. All right, so pi over 6 corresponds to radical 3 over 2. I don't know why I wrote a pi there. Radical 3 over 2. Then sine of pi over 6 is 1/2. And then we have, again, a radical 3, a pi over 6 is what I meant to say. I almost said radical 3 over 2 again. So you look at this and say, well, I don't know if this is really worth it, but you do have the decimal values there to play off of. So you can kind of make do with it. All right. So the issue here is, again, I would like to have that t value in there, but it seems to kind of mess things up. All right. So there's no real answer for that. All right. So pi over 4 isn't really convenient for either of the functions, although you could include it if you want, but I tend to want to skip that. So pi over 3 would be my next one. So 1/2. Oh, sorry. That was funny. It's 2 sine of t. So I had the 1/2 there, but it should have been a 1. So pi over 3 will give me a 1/2 and then a radical 3. And then, just to kind of cap it off for the first go round, you may want to just throw in a pi over 2 and then stop and take a look around and see where we're at. 0, 1, and then pi over 2. All right, so we want to plot these in vector form, right? So just for the sake of sanity, I won't write them out as vectors again. What I'll do is I'll just write the first one out as a vector, 1, 0, 0. But it's understood that the rest would also be vectors, right? So I would just need some decimal equivalents for some of these, in terms of the pi over 6 and the pi over 3. That just seems like a side calculation that I would perform. So, just kind of off on the side here, pi over 6. That's about 0.5-ish. Pi over 3 should be double that, so a little bit over 1. And pi over 2 is about 1.57-ish. So pi over 2. So we have these numbers just kind of in our pocket so that when we're plotting, we know what we're plotting. So 1, 0, 0. So I'll go out one, and I'll take note of what the largest value is in terms of x. 0.8-ish is what radical 3 over 2 is, 0.86. So I'm going to just go out 1 unit here in each direction for x and y. And then, for the z direction, we have to go in terms of pi. So we're looking at pi over 6, pi over 3. Right? Pi over 3 is double pi over 6, so that's fine. The next one would be 2 pi over 3. Actually, no, it wouldn't. It should be pi over 2. And then 2 pi over 3. 30, 60, 90, 120. Right? So we have those metrics included, so we're good there. Now it's just a matter of getting some points down. So 1, 0, 0, 1 in the direction of x, no movement in the direction of y or z, so that's perfectly fine. We do need the vector corresponding with that. Right? So I'll just chuck in the vector here and just have it ready to go. All right. Then about 0.9-ish in the direction of x, 1 unit in the direction of y, and then pi over 6 in the direction of z. All right. So let me bring that in here. So I'm just going to estimate this. Feels like it's about 90%, that distance there. Let me see if I could just snag that. I might have to disassociate it with the, oh, I got it. Okay. 1 unit in the direction of y, and then pi over 6 units up. All right. So that gives me my second point. But again, I'm connecting it with a vector to the origin. All right. So then next up is 1/2 and then radical 3. So that's 0.5 units in the direction of x, about 1.7 in the direction of y. Only plot a 2 here. All right. So 0.5 in the direction of x. Get that going here. Looks like it's about like that. Oh, little arc. I don't want that. And a little off. Let me do it on this side. Could be right. Corresponding with about 1.7, I'm going to eyeball that to be about right there. And then we're going up pi over 3 units. And connecting that to the origin with a nice vector. Then 0, 1 pi over 2. That's like a relief, 0, 1, and then pi over 2. So 0 in the direction of x, 1 unit in the direction of y. So then we're just going pi over 2 units up. Right? So let me get pi over 2. And at this point, if you don't have the trend, the 1 unit in the direction of y, if you don't have a sense of the trend, then you keep going with more points. But it does seem like this curve is going to wrap around. So if I start here, it seems like it's going to kind of pick up on, something like that. And then it's just a matter of getting some more points. But it does look like it's taken on the shape of something along the lines of a roller coaster. You know, it's kind of got that feel. So maybe we'll grab another point or two and see where this gets us. So the next one would be 2 pi over 3. Cosine of 2 pi over 3 is negative 1/2. It would be negative 1. I'm sorry, negative rad 3. Oh no, it would be positive because it's the second quadrant. But still the same height. But then it same y value. I mean, but the height is going to be double though. All right, so got a little funny business going on here, but nothing too crazy. We can put it in the table too to verify. So 2 pi divided by 3, negative 1/2. Then scroll over, you see the 1.73. All right, so half a unit in the direction of x, but backwards, right? And then 1.7 in the direction of y, and then 2 pi over 3 going up, right? So what I can do here is I can get a little kooky. We're just going to hang on to this. That's the 1/2 unit in the direction of negative x. In the direction of y, we're still going 1.7 in the positive direction. So this is just telling me I'm going that away. And then we're going up. Just double checking. Something didn't feel right there for a second, but I might be just imagining it. Not a little too thick. All right. So then I would plot the point here. And then we would get something more substantial, but something really actually doesn't feel right. Oh, 2. Son of a gun heck. Pi should have been 2, and I wrote a 1. I don't like it when that happens. It should have been a 2. So this other point here, I can do a quick fix. Get rid of this, delete. This one should have been here. And now it all just looks so much better. All right, but it does hopefully start to look like maybe it's an ellipse that's growing in height, right? So you can sort of get an idea that perhaps it's going something like this, you know, but really the idea is to just get a sense of the trend, all right? So what I'll leave you with for tonight is this problem here. It doesn't seem like I even remotely prepared you for it, but if you really think about it, it's going to set us up for the calculus stuff, domain restrictions on this vector value function. I'll give you a little tip. The domain restrictions are the same as they've always been, right? So if part of the vector value function is undefined or indeterminate or something like that, imaginary, then you can eliminate it from the domain, and that would be a restriction on your function, right? So that's where I'm going to leave you this evening. Got my next class coming up. So if you have any questions, you can, at least this time around, because I took you right up to the end, unfortunately. I seem to be doing that a lot. I'll have to tone that down. But yeah, you can ask through a reminder through email, all right? And I'll try to get back to you, all right? But I gotta jump off right now. I apologize for that. So I'm gonna stop the recording.